Thank you very much. Good morning, everyone. So yes, my name is Zohreh Davoudi. I'm a nuclear theorist at the University of Maryland, College Park. And I work at the intersection of nuclear particle physics and quantum information science. But in my past, I also have done quite a bit of classical computations for nuclear and particle physics. So what I'm going to try to do today is to give you a perspective of what we can do with computation in general in nuclear particle physics, and why we think that we need this new quantum technology to be able to solve even more problems in this field. So there are two parts to the lecture. Obviously, there's a 90 minutes lecture number 1 and another 90 minutes lecture number 2. The way I decided to divide material is that in the first lecture, I will give you sort of a bird's eye view of the field. So it's more like a colloquium style, so that for those of you who are not in this field, you will get an idea of what are our problems, motivations, what progress we've made so far, what needs to get done in the future. So in case you got interested, you also have sort of gotten a sense of what are the future directions to work on. In a second lecture, then we will deep into some of the details of this program, understanding, and this is lecture number 2. Okay, sorry about that. So you already see the topic of lecture number 2. We're going to see examples of lattice gauge theories and how to simulate them, which is really the topic of this lecture. So let me go actually to lecture number 1. Okay, and then I start there. Okay, better. So before I start, let me ask, how many of you are in the fields of either nuclear physics or particle physics, or in other words, high energy physics? Okay, not a lot. So that means that I have to maybe go a little bit slower and try to make this lecture as introductory as possible. That's my goal. And please, please feel free to ask questions. All right, this is a very multidisciplinary school. So the goal is that everybody would get something out of this. All right, so I don't want everybody else to tune out and only a few people that care about this field to listen to me. All right, that's not the goal. Okay, so let's start. Really, what we are trying to do here is to simulate fundamental particles and forces in nature from the most fundamental level, from the underlying sort of interactions that are described by the standard model. Now I'm going to tell you why and how, okay? And the reason for the lecture being the simulation of quantum field theories is really because at the end of the day, these fundamental particles and forces are described by quantum field theories of nature. So in order to be able to simulate, make predictions for nature at a very fundamental level, we need to know how to quantum simulate quantum field theories. If you don't know what a quantum field theory is, I'll give you a sense of what that is and what are sort of the differences with the sort of the usual quantum mechanical descriptions that you may have in mind for many of the problems that you care about. So this is really sort of an overview of what we care about in this program. As I said, at a very fundamental level, we know that particles and forces in nature are described by a beautiful mathematical framework called a standard model of particle physics. It took many, many decades of both theory and experimental work to be able to realize what is really at the most fundamental level, constituting the fundamental structure of matter. And as you can see in this picture, we have a bunch of different particles and a bunch of different force carriers. 3 of the fundamental forces in nature, including a strong force, weak force, and electromagnetism, really fit this mathematical picture. Unfortunately, gravity does not. On the other hand, gravity at many scales is much weaker than the other forces in nature, unless you think about black holes, right? But we're not going to think about black holes in this lecture. So it is really sufficient to think about these 3 fundamental forces that are described by a bunch of quarks, leptons, their antiparticles, as well as the force carriers, the gluons that carry the strong force, and then the gamma, the photon, which carries the electromagnetic force, as well as these massive W and Z bosons that carry the weak force. Okay? And the center is sitting the Higgs particle, which is responsible to giving mass to any particle that has mass in this picture. Some of them don't, but the ones that have, all of them coupled to Higgs, and as a result, they gain their mass. So this is really great. And we know that the mathematical picture that would describe this is called the quantum field theory. Really underlying symmetries are a bunch of gauge symmetries, SU3, SU2, U1. If you don't know what that is, we don't need to worry about right now, okay? So now how do we go about from this framework and start to make predictions for what we see in the universe, right? We know that at the end of the day, those simple equations of a standard model that I didn't write down, but they are there, they are confirmed in high energy colliders and a bunch of other experiments. We know that this is the underlying interactions and particles. How do we go about and make predictions for the interior of a neutron star? What are the different phases of a very dense form of matter? What would happen if you collide two high energy particles? How would particles would produce out of that very extreme set of initial conditions? And more importantly, what would happen in the early universe? Because the reason we do some of these experiments is really to mimic conditions that occurred after the Big Bang so that we can understand how matter evolved and equilibrated to the universe that we have today. This is very dynamical non-equilibrium process. In the end, we know that these forces and particles have been really at the core of what has happened. But how do we go and make predictions for these complex systems, starting from those first principle interactions? Okay. So the way that we would like to do this is using simulations, because unfortunately, analytic work can get us somewhere, but not really all the way to be able to make these accurate predictions for a complex sort of many-body or infinite-body physics that we're after over here. So simulation is the way to go. We either have the classical simulation path, or as we know today, quantum simulation path as well. With classical computing, we have made some progress in understanding various aspects of these different physics topics, but we're still very much limited. And in fact, now this is kind of the reason that we think quantum computers and quantum simulators may start to give us more insight about the nature of these processes, is starting from the fundamental level. So we're going to leverage quantum superposition and quantum entanglement to be able to quantum simulate these really quantum processes that we see over here. And the idea is that maybe along the way, we learn something more about the underlying interactions themselves. Using principles of quantum information theory, quantum entanglement, maybe there is more to these underlying interactions that we didn't discover. We always think about symmetries to give us sort of those organizing picture of fundamental forces and interactions. And nowadays, people think that maybe there is more fundamental principles like minimization or maximization of quantum entanglement that really underlies those symmetries or those emergent symmetries. So there are a lot of cool discussions also on that front in the community that I'm not going to cover. Okay? So this is really the overview of this program, and I'm going to give you bits of pieces of where we are and what we can do with it. If you really are interested more, I have given several references here. This is a shorter review article in Nature Physics that you can look at to get a sense of some of these problems, and some longer discussions and trying to sort of set the path and roadmap for the program. You can see in some of these community white paper and planning documents that you can read. Okay? Any questions so far about what we're going to do? All right. Yes.
Can you explain what is gauge group or what is gauge?
We get to this a little bit more in the second lecture, but yes, I can tell you a little bit more about what the gauge group is. So what is your background, so that I can use an example based on mathematics? Yeah, so symmetries, right? So symmetries are really fundamental properties of physical systems. And there are two types of symmetries. One is a global symmetry. For example, you can have the total electric charge in the universe is conserved. The total number of baryons in the universe is conserved. In chemical systems, right, you still have sort of a notion of the global charge, whether that's the number of particles or again, electric charge. So these are what is called like global symmetries. Now, it turned out that for describing these fundamental interactions of nature, we also need to promote that concept of global symmetries to what is called local symmetries, meaning that not only that at every space-time with the global symmetries, at every space and time, you take your objects and you transform it in the same way. So this is like a global change to the system. And under those global rotations or changes to the system, certain quantities remain conserved, according to Noether's theorem. Right? However, you can say that I want to do local transformations. I'm going to take this space-time point and rotate it in some way, take this other point and rotate it in some other way. And now, we don't have the concept of those conserved charges anymore because this doesn't fit into the Noether's theorem for conserved charges. It actually introduces redundancies in the description in a sense. So the gauge symmetries are a way for us to describe the number of physical degrees of freedom that we see, for example, coming out of the photon interactions in nature. You look at the photon interactions and you see that photons are only transverse. They cannot be longitudinal. They cannot be like temporal. So there are like 2 degrees of freedom to the photons, right? And then you start to describe this picture, you always start from 4 degrees of freedom because we're living in 4 space-time dimension. And then you realize that if you incorporate these like local symmetries, then you can incorporate them in such a way that in the end of the day, you have 2 degrees of freedom that are physical, and there are like 2 degrees of freedom that are redundancies. So that's kind of the notion of the gauge symmetry. Why nature decided to be described by these gauge symmetries, we don't know. It is what it is, right? And the interesting point is that there are also 2 types of these gauge symmetries. The ones that are abelian type and the ones that are non-abelian type, okay? So the abelian ones are responsible for things like electromagnetism. The non-abelian ones are responsible for things like the strong force. The difference between abelian and non-abelian is, again, the generators of these symmetries either commute or don't commute. Again, why nature decided to pick both types of abelian and non-abelian gauge symmetries to be described by, we don't know, right? But this is how sort of in the 20th century, people started to kind of go and discover more and more particles, look at their properties, and understand that they belong to different sort of, in terms of their properties, they can put them in different categories. And then they looked at them more carefully from a mathematical perspective, and they discovered that they actually like belong to multiplets of some of these gauge groups and so on. So it is a beautiful story, right? But unfortunately, we don't have a lot of time to go and sort of really drive all these equations of the standard model. But that's a very good question. We will talk a little bit more about this in the second lecture when I show you examples of this gauge theory. Okay? In the end of the day, the gauge bosons are described by bosons, really. Sort of there's gauge degrees of freedom. But they're also like fermionic or matter degrees of freedom. So these theories are coupled fermion-boson theories that we are trying to describe by this picture. Yes?
So follow-up question. Look like your notation, you have 6 degrees of freedom. You have SU3 times SU2, U1. Does it mean you have a 6 dimension?
No. It's more than that, right? So you need to count the generators of each of these groups. Okay? So for example, here you need 8 gluons. Here there are 3, and here is 1. So there are 3 plus 1, so there are 4 over here and 8. So this G, actually, there are 8 types of them. And these 4 are really representing these 4 generators. Okay? Okay, good. Anything else? All right, so now I told you that over the 20th century, people learned quite a bit about this picture. How did they like really put the pieces of puzzle together to get to the standard model, right? It turned out that a huge part of it comes from scattering or collision processes. They built bigger and bigger colliders with higher and higher energies. They were able to smash particles together at the level where they kind of disintegrate to their constituent particles. And as a result, you can kind of learn something about the internal structure and so on and so forth. So it would be really exciting to be able to describe these high-energy scattering processes from a fundamental level using our simulation tools. Let's say that we can do that. Then we probably won't need to build billion-dollar experimental facilities to do particle collisions. How cool would that be to be able to do it on a tabletop quantum computing experiment, as long as we have these fault-tolerant quantum computers, right? So that's kind of the idea, but that obviously that is very complex. And today I'm going to show you how complex that problem is and how large your quantum computer should be to be able to compete with a large hadron collider machine. Okay, so that's the idea. All right, so here are a few examples of why these scattering processes are pretty important, would tell us something about nature. Well, first of all, they teach us about the internal structure of matter. If someone would tell you a proton, what is inside a proton or a neutron, right? Obviously, protons and neutrons are at the core of atomic nucleus, but themselves, they're built out of these fundamental quark and gluon degrees of freedom of the standard model. But in what way? How do the quarks and gluons distribute themselves inside this object? How do we learn about that? In fact, in the US, we're building multi-billion-dollar experiment called Electron Ion Collider, or EIC, that is going to really explore this question. Just give me a proton, I'm going to tell you what is the internal structure of the proton using this multi-billion-dollar experiment, right? So that's still a very relevant question in 21st century. Constrained astrophysical models of stellar evolution and terrestrial energy production mechanisms. Because these are scattering processes, in the end of the day, they are nuclear reaction processes. And we'd like to know the rate of some of these nuclear reactions very precisely to be able to understand how the stars like sun would evolve throughout their lifetime, and how to come up with sort of better, maybe fusion facilities to get energy out of these reactions. So understanding the precise rate of these nuclear reactions is still very important as of today. Okay? As I said, we would like to understand how matter evolves under extreme conditions, such as after the Big Bang. And that's why we collide these particles with very high energies. We're trying to mimic the conditions that occurred after the early universe, so that we can understand how, for example, like atomic nuclei came about, and even like much earlier, whether there were some exotic phases of matter like quark gluon plasma or something else that really came about and cooled down and gave us sort of the universe that we have today. We would like to be able to reproduce those conditions and be able to make first principle predictions as what to expect at any given time during the evolution of the universe. And importantly, it has led to many discoveries. And even today, we are really pushing to make the next big colliders, right? Because we know that there are stuff beyond the standard model we don't understand. There's like dark matter. There's like this question of why so much matter in the universe and not so much antimatter, although standard model interactions are very symmetric with respect to the matter and antimatter production and annihilation. But still, we exist today because we're built out of matter and there's no antimatter. Otherwise, like we all annihilated into essentially light, okay? So there are so many questions that are not described by the standard model. We know there is more. We need to increase the energy. We need to really sort of try to excite these new particle excitations and discover their properties. And that's why we're still, into today, we're building these colliders to be able to discover new symmetries, particles, interactions, and so on. Okay, so these are some of the most fundamental questions that in the field of nuclear particle physics people are after. Really understanding the underlying structure of matter, all the way to the level, to the constituents that we don't even know exist, but we're trying to find them, okay? So now a barrier to making first principle predictions for these systems is the fact that these systems, first of all, they're big, they're complex, there are really many body, or sometimes like infinite body if you think about these quantum field theories. It's the fact that they are quantum in nature, they're relativistic in nature, and they're also sometimes non-perturbative in nature, okay? So everything that makes a theoretical problem complicated is in here, okay? So we use quantum computers as an application of a quantum computer. We always say solving quantum mechanical systems. These are not only quantum mechanical, but also relativistic. And in many applications that you probably work with in quantum chemistry, material science, and so on and so forth, you probably think about non-relativistic quantum mechanics. And I will tell you a little bit about the differences between relativistic and non-relativistic simulations in a moment. There was a question, yeah.
What do you mean by non-perturbative in this context?
I'll give you an exact example in 2 slides. Very good, okay? The non-perturbative aspect is really sort of a feature of the strong force, the quantum chromodynamics, okay? And I'll tell you what quantum chromodynamics is. In the end, it's a quantum field theory of quarks and gluons in the standard model picture, okay? So if everything would have been maybe weak interactions or electromagnetism, things would have been much simpler, because for most of the energy scales, they are pretty perturbative because the interactions are weak. You can do analytical work, perturbation theory, to get a sense of what you should expect. But with a strong force, unfortunately, that's not the case. So, and a strong force really is at the core of all sort of these scenarios that I mentioned. We really have to have a control over the strong force and its predictions to be able to learn something about these processes. So what is the strong force? I want to show you an equation without even describing it that much. But at least for those of you that may have thought about quantum field theories, but not to the extent that have seen a QCD Lagrangian, I think this is helpful. All I want to say is that the Lagrangian of QCD, which is part of the standard model, can be written in 2 lines. It has 3 different parts. A part that describes the kinetic energy of a bunch of quarks of different flavors, up quarks, down quarks, strange quarks. There are 6 of those types of quarks in nature. And so that's this F index that goes from 1 to the number of flavors in a standard model. So as I said, there are 6 of them. But depending on the energy of the process, you may not have to care about the very heavy ones, okay? But in principle, there are only 6 of them. Each of them comes with a non-zero mass. We know that for sure, okay? Some of them are very light, like the up and down quarks. They're just a few mega electron volts. Some of them are very, very heavy, okay? Like the bottom quark. This part would tell you that the gluons and these flavors of quarks, they would talk to each other, they couple through this gauge invariant coupling. Okay, so the gauge symmetry really comes here, so I won't go into this. This index I would tell you that there are 8 numbers of these gluons. That's what I mentioned, right? For SU3, there are 8 of these gluons, and there are 3 types of colors, and that's why it's called chromodynamics, because it's SU3. So there are 3 different, what we call colors, okay? So each of these quarks has a flavor, but it also can have a color associated with it, okay? And then each of these gluons, there are like 8 types of them associated with 8 generators of SU3. This complicated form over here is just to tell you that the gluons themselves also talk to each other. It's very different from electromagnetism. Photons won't directly interact. We know that, right? And so there's no self-interactions of photons in nature, but there is self-interactions of gluons in nature. There's a very distinct feature of a strong force compared to electromagnetism. It actually comes from the fact that electromagnetism is abelian. As I said, it's like a U1 gauge symmetry. This is a non-abelian gauge symmetry. So because of non-commutations of the generators, you produce interactions between the gluons. And it turned out that this feature by itself really changes the phenomenological behaviors of many things in the theory compared to electromagnetism. Just these terms, if you just like work them out in your calculations, you are going to find out, for example, that this theory is actually pretty strong at low energies, which is very different from quantum electrodynamics. I'll tell you a little bit more about that in a moment, okay? So this is it. You don't need to know more about what these like mathematical notations and so on are. I just want to say that we exactly know what the equations of a strong force would look like, all right? There's no mystery there. And as a matter of fact, if you look at the entire forget about the weak force, which doesn't matter in many of the processes that we care about in for example, nuclear physics. Let's just think about electromagnetism as well as the strong force. We will see that in terms of the input parameters to this strong force, there are only NF plus 1 number of parameters for QCD. And then let's say for QED, there is just one coupling. And maybe the mass of the electron, you can also add that. Where does that N sub F plus 1 comes from? Let me go back to this previous slide. Well, give me the masses of the quarks. There are NF number of them. This is an unknown parameter that you have to kind of measure to start your calculations. Give me the value of this coupling, and that's it. If you give me NF number of masses and the value of the coupling, then I can, in principle, make predictions for everything else. That's as simple as that. It's just really minimum number of free parameters. You may ask me where these parameters come from. How did nature decide to set the masses of the quarks the value they are? I have no idea. Particle physicists are trying to come up with models of beyond the standard model that would describe this particular masses of the quarks. If they are composite objects themselves, maybe the masses come from those like interactions at the internal level. At the moment, we don't know. We say these are free parameters. Nature gives us these parameters, okay? But that's the beauty of this model. With a very few number of parameters, a lot of complexities already arise at the many-body level, okay? Number 2, which is important, is QCD is asymptotically free, and the running of the coupling as a function of energy, which is a feature of these like quantum field theories, is that the coupling constant is not really constant. It runs as a function of energy, meaning that at a high energy and low energy, you may have very different values of the coupling. And it's not arbitrary. You can actually work it out in perturbation theory, at least at high energies, to be able to predict as a function of an energy this value of the coupling constant. How does it change with this sort of constant mu prime? So forget about all these equations that is written here. I want to just show you a plot of what this means. So again, the coupling constant now as a function of some momentum q, which is related to the energy. And this is that q as a function of giga-electron volts. So you already see this feature that I mentioned. The coupling constant at very low energies is order 1. It's pretty strong. As you go to very high energies, it becomes pretty small, okay? And there are many data points on this plot. Some of them come from experiments, some of them from perturbation theory at higher orders. Some of them actually come from non-perturbative lattice QCD calculations that I mentioned in a moment. So we have a very good confidence that actually not only at very high energies when we can do perturbation theory, but also at very low energies when we do non-perturbative calculations or experiment, this is really the feature of QCD. If you plot this for electromagnetism, for QED, you see kind of a feature that looks like complete opposite. It goes this way, okay? So that's why a strong force and electromagnetism are so different, okay? So at high energies, the theory is asymptotically free. At low energies, which is actually pretty important for many of the processes that I mentioned, QCD is non-perturbative. You can't really do a perturbation theory in the coupling constant to be able to make predictions. You really need infinite orders in coupling constant to be able to make predictions. And therefore, we need to solve the theory kind of exactly without making approximations and couplings or anything. Yes?
What's the definition of alpha? I didn't see
Alpha is g squared over 4 pi, and g is what was in the previous slide.
I see.
This g. So G squared over 4 pi by convention is called alpha. Good question. It's just a coupling constant. Yes?
And it's also called the G factor, correct? Is that the same?
No, G factor is something else. G factor is related to magnetic moment and then a spin. Yeah. All right. Okay, so does that make it clear what non-perturbative means? Essentially, I can't take this and say, all right, yes, these are like very complicated. Let me just look at the linear order in G in my calculations, or maybe second order in G, and forget about everything else. We really need infinite order in G to solve this problem. Okay, so now let me just tell you a little bit more about the wonders of these strongly interacting quantum field theories. So essentially, the equation that I showed you was like very simple looking, but as I said, really the complexity is in non-perturbative feature. You have to really solve it all the way to be able to learn something about the physics. So as I said, we're trying to understand something as simple as a proton. Okay? Just we know proton has some mass. It has some electric charge, positive 1. It has a spin 1/2, right? Like at macroscopic level, it looks very simple. But if you think about it, we don't actually quite know where the mass of the proton like come from. We do, right? But we have to do like non-perturbative calculations to be able to learn that. And in fact, there are really amazing calculations that are able to do that now. Why? Because if you think about it, if you go back to maybe your high school courses on particle physics or just like Wikipedia, it would tell you that a proton is made out of 2 U quarks or up quarks and a down quark. You say, all right, that's simple. There are like 3 quarks. And then you add the masses of these 2 quarks. That gives you only 1% of the entire mass of the proton. Where does the rest of the mass come from? If proton is as simple as 3 quarks, that shouldn't be the picture, right? But the proton is actually like these 3 valence quarks, and everything else could be the quarks and antiquarks that always pop out of the strongly coupled vacuum and then annihilate to the gluons. The gluons then like interact with everything else. So there is a sea of infinite number of possibilities, as well as these like 3 valence quarks. And really, the dynamics of these quarks and gluons and antiquarks is what makes the 99% of the mass. So these non-perturbative effects are very important. If everything would have been perturbative, we would have been able to describe the mass of the proton much more simpler. Okay? The same goes with the spin of the proton. In this case, you say, all right, I have 3 objects. And then all 3 quarks have a spin 1/2, so maybe 2 of them really paired to a spin 0, and then there is like 1 spin, so I get a spin 1/2, simple, right? But then you say, oh, wait a minute, there's all this dynamics of the gluons and quarks and antiquarks, and they have a spin, they have orbital angular momentum. It's a mess. How these like angular momenta would add up to give you a spin 1/2? And then again, you go and do this non-perturbative lattice QCD calculations that would take really hundreds of millions of CPU hours to do. And then you realize that, no, that's not that simple, right? You realize that a good fraction of the spin of this object comes from the gluons themselves. So there are a lot of like mysteries and that we are starting to actually learn now about these internal structures, being able to do non-perturbative simulations of a strong force, okay? So I mentioned too many times these non-perturbative methods. I'm going to tell you a little bit more about what that is, yes.
So how about the spin of the quark itself?
The spin of the quarks in the standard model are fundamental particles. They're fermions, a spin 1/2.
It's intrinsic.
Yes. Maybe quarks at the fundamental level are not really point particles either, and there's like a constituent subparticle that we have to worry about. But from the perspective of a standard model, they're point particle, they have a spin 1/2. The gluons are spin 1 objects. These are vector particles. And just like with the photons, and that's it. Okay? All right, so as I said, we can't do any perturbation theory, but really we have to have something else. What is that? Well, the option that is available to us is called the method of lattice QCD, or lattice quantum chromodynamics. What that is that you start from the Lagrangian of QCD that I showed in the previous slide and say, all right, let me forget about the continuous of a space and time. Let's think about the finite extent in time and space. So let's think about the cube, for example, or hypercube in this case. And then also discretize it, so that I don't have to worry about these quarks and gluons everywhere in a space and time, rather on a finite set of points or links between them. So that would make the problem finite dimensional as opposed to infinite dimensional. Okay? So put the quarks on these points. So I have a picture over here. Put the quarks, whether they are up quarks or down quarks or they're anti-quarks, they put them on the points on this lattice, and then put these gauge bosons that I have represented now with this parallel transporter, so that it has a relation with the A mu field that I showed before, put it on this one. Okay? So we have both gauge bosons on these links, and I have all the quarks at these points. Okay? So this is the setup. And we know about this framework since 1970s with the work of Ken Wilson. All right? So it started at the time that there wasn't really enough big computers, classical computers, to be able to do any reasonable calculations of this sort. But people still started to figure out all the theoretical algorithmic requirements of this program. And step by step, as the computers became larger and more reliable, they started to do bigger and bigger calculations. Okay? And so now let me give you examples of what they have been able to do with this method. So obviously, I didn't say much about how we actually do these lattice QCD calculations. In the end of the day, obviously, you have to take infinite volume limits, zero lattice spacing limits to be able to describe nature. But we have ways of doing that, right? By doing multiple calculations, analytical understanding of some observables. So there's a lot of details and decades of progress that have led to very impressive calculations. So let's say we have now this method. Can we do a scattering? I told you that my goal is to be able to do this scattering of particles, because that's really important. That gives us pretty much everything that we care about in nuclear particle physics. So can we classically simulate a scattering of composite particles from the standard model? So the answer is a partial yes, but unfortunately, like in very limited scenarios. All right. So we can use this method of lattice QCD or lattice gauge theory, which is based on Monte Carlo sampling in Euclidean space-time or imaginary time, to be able to make predictions for low-energy scattering processes. So we can do a little bit of dynamics. These are real-time processes we're talking about. So that's amazing, right? Despite the fact that we only are able to do imaginary time simulations using Monte Carlo, and I tell you in a moment why, and we still can get a little bit of information about dynamical processes. That's amazing. And in fact, there's a very beautiful mathematical framework for how to do this. Yes?
So, I mean, you know, in condensed matter, it's because we're taking thermal averages. Why does this wick rotation work in QCD to give us?
It's exactly the same thing. Okay. So we turn this problem into a statistical mechanical problem because we're going to Euclidean time. So that's why we kind of lose the notion of Minkowski wave functions and states and Hilbert spaces. Unfortunately, we don't have that anymore. We have a bunch of statistical samples, and certain quantities are still derived from those samples, like the masses and energies and so on. Same between Euclidean and Minkowski. There are certain quantities that are not, like these dynamical correlation functions, but it turned out that there are a few tricks that will allow you to still do that analytic continuation in it. You still don't do the analytic continuation. You go like in a very indirect way. If you have heard about it, Lucher's formalism is what allows you to extract some of these dynamical information still from these Euclidean correlation functions, but that's kind of the trick. There was one here, and then I'll go back. Yes?
It's be a very silly question. Why do you use rectilinear QCD? Can you use polyhedrons and others that are like a...
Yes, you could. You could. It just makes So generating these ensembles, these statistical ensembles on these lattices is very costly. So usually it would take years of production on supercomputers to just get a few ensembles with a given geometry, and every other collaboration would use it. So we share these ensembles together. So now if someone would decide, I want to change the geometry and look at something else, you have to like develop the whole thing from the beginning and generate these ensembles. And if other people are not on board, then you're in trouble, right? Because these are very expensive calculations. But it's a choice that is simpler and everybody is used to, and all these codes that are developed to generate these ensembles are based on that particular geometry at the moment. Yes?
So can you explain the idea behind Euclidean time for simulations, and how does it deal with, say, local symmetries, CPU symmetry?
Local symmetries, they won't change, okay? So in terms of now your time is imaginary time, all those transformations would be the same between Euclidean and Minkowski. So in fact, we do this in a way that we don't change those kind of important gauge symmetries and the global symmetries. There are certain symmetries that are broken, like rotational invariance or Lorentz invariance. And as long as you're aware of that and you make sure that you recover the right continuum limits in the end of the calculation so that those corrections to rotational violations would go away, then you're in business. So it's very important to keep track of the symmetries that you preserve and the symmetries that you break and eventually would recover. So that's a very good question. But definitely, there are certain symmetries that are preserved. We preserve gauge symmetry with this construction, but we can't do anything about the Lorentz symmetry until very end when we take the continuum limit. Okay? All right. We're going very slow, but I think it's good, good discussions. So that's okay. So let me give you two examples. Remember I told you how complicated a proton is? Not only now we can compute the proton itself and get its mass correct, get its spin correct and everything, but we can also do proton-proton scattering or reactions from quark and gluon degrees of freedom. It's not an easy calculation. It actually, so this is like just being self-serving. I'm showing two results from my work, but of course it's a big community. A lot of people are doing really amazing work. But I just want to tell you that something like a proton-proton fusion on a classical computer, it took us about, I think, 200 million CPU hours, about 2 years of runs. And we even put a dollar amount for this based on the computational resources that we got from the agencies, about $1 million. So $1 million calculation, classical computers can give you the rates of proton-proton reactions from underlying a standard model. Why is this important? Because we can't really do experiments to get this. It's very low energy. It's a weak process. You can't really put these like protons with a Coulomb barrier close to each other at very low energies and then measure their cross-section. It's really almost impossible in an experiment. So we have to do a lot of indirect ways and using other probes, other methods in experiment to get a sense of what are the coupling constants at the nuclear level that are associated with this, and then turn that into predictions for solar modeling, for example. So there's very huge uncertainties on the reaction for this process because of what I said. And then with this Lattice QCD method, we're starting to kind of lower that uncertainties, okay? So that's amazing. Not only that, we are also able to do processes that you cannot do in experiment at all at the moment. For example, turning 2 neutrons to 2 protons and 2 electrons without any neutrinos. This is something that breaks the standard model. It would tell you that neutrinos are of Majorana type. They are their own antiparticles. And in fact, we're searching very vigorously for a process like this. Again, we're building billion-dollar experiments to be able to search for neutrino-less double beta decay in atomic nuclei. It's very important to know or get a sense of what is the expected rate of this reaction and in what atomic isotopes we should look for it. So the underlying level, we should go all the way and calculate the rate of these reaction processes. And again, we have used the method of Lattice QCD to be able to do the first steps towards these calculations, right? So this is amazing. This tells you that you can do a little bit of dynamics using classical supercomputers It's still for these very difficult, non-perturbative standard model problems. Okay? There was a question. Yes?
You sweep, like, so for the Majorana phase of the neutrinos, do you do sweeps at the lattice, or do you leave the Majorana there?
Majorana phase of?
Well, I mean, if you write the Majorana Lagrange, there's like if you have make an axis of being Majorana.
So the Majorana bit is not the non-perturbative bit.
No,
So that bit, so there are two parts to the calculation, the leptonic part and the strong interaction part. And they are convoluted through an integral.
Yeah, I'm asking about the leptonic part.
The leptonic part is analytic. You just take care of it analytically. The strong interaction part is non-perturbative, but it's actually pretty related to the leptonic part because the energy of the neutrino that is being swept, that's very important. So you have to like do this for all the energies, and to do this integral. Exactly, we're simulating the hadronic part. Very good. Yes?
Yeah, so in the first calculation, so the number you get, like, is it used to define your other models or other calculations?
Which one?
In
This
the first calculation, yeah. So what are the applications of this, like this calculation?
So the application of this is that we calculate directly the rate, and then we turn this into the coupling constant in an effective field theory that is based on nucleons and protons. And those couplings then would feed into these reaction solar models to make predictions for the rest of the chain of the reactions that are happening to give you sort of the energy production in sun. Indeed, so we're providing an input to the next level. The same here, we're providing the input to the next level. But without this, we can't even start, right? So this is the idea. Yes?
Since you said that like it's very hard to experiment them, like how do you kind of like verify like the simulation results, or like how do you know that? Like
that's the idea, right? So you really need the theory to be able to make predictions. Like there are situations when you have experiment and you do the theory to confirm experiment, that's great. But what do you do if you don't even have experiments? And then theory is your only tool to be able to do, just like, for example, you've probably heard of anomalous magnetic moments of the muon. There was an interesting experiment at Fermilab, and there was a previous experiment at Brookhaven Lab. The results kind of matched. And the reason that they redid the experiment was that some of the theory calculations said that there is a kind of mismatch between theory and experiment, and therefore there must be new physics beyond the standard model to describe it. So they redid the experiment, and theorists redid the theory, but not with the previous methods. They were kind of mixed with some experimental input, but rather with this very first principle lattice QCD calculations. A few months back, they introduced their results. It kind of matches with experiments within error bars. So it seems like there is no discrepancy anymore, right? So sometimes we do the theory to confirm experiment. If it's not confirmed, that means that maybe there is something else, there is new physics. So it's very important to do those confirmation tests, right? Sometimes, like in these processes, we don't even have the experimental input, right? So, and if we don't have the theory, we can't even start to make predictions for something else. So that's why the role of simulations, non-perturbative calculus is very important in our program, okay? Good, all right. So it seems like maybe we are all set, but unfortunately not. Yes, Ken.
So like you were mentioning, when Wilson first thought about these things, it was impossible because the computers were
Yes, yes.
So from the original kind of muon anomaly to theory agreeing, is it mostly just the computers got better, or is there actually a fundamental change in the way we do the lattice calculation?
Both, definitely both, right? Without these supercomputers at the pettascale and exascale, we can't do this, so forget about it, right? But there were a lot of theory and algorithmic developments that really made things possible. For example, we didn't know how to put fermions on a lattice without breaking chiral symmetry. And that turned out to be important for some of these like physics problems. So people had to think very hard about how to discretize fermions such that we can still keep their chiral symmetry as we take the continuum limit. We didn't know how to do these reaction processes, these scattering processes, until Martin Lucier thought about how to indirectly map these Euclidean calculations to the Minkowski calculus. That was a really impressive theory work, right? So there's been a lot of like theory and algorithmic developments. Otherwise, we would have been very limited doing maybe single hadron quantities and so on. But I would say definitely both. And I feel like for quantum computing business, we definitely need both as well. Yeah, good question. Yes.
On the last slide, I'm sorry, maybe I missed this. What sets the uncertainty in the calculation for the proton-proton fusion?
So this one. So there is a piece that comes from essentially the interactions of the weak currents with a single nucleon. So in a proton-proton fusion, you can have the weak current that interacts with each of the protons and turn them into a neutron and some other leptons, right? So if you only account for those single current interactions, then you essentially get 98, 99% of the reaction right. And then that 1% that comes from the coupling of the weak current with the two nucleons at the same time, that's called a short distance contribution. It's about 1 or 2%. And that's the piece that is pretty uncertain. And you may say it's like 1 or 2%, why do we care? It turned out that it propagates to the calculations of these solar models, and it turned out to be very important. So not only we have to do these calculations right, we have to do them at the percent or sub-percent level. Okay? Good question. All right. So we are not, unfortunately, all set despite all this progress, because how if I want to go to higher energies, like energies at the Large Hadron Collider? There, I can't just have like two low energy processes, two particles coming in, maybe 2 or 3 coming out. Those things we can handle. Unfortunately, if you're producing abundant number of particles and maybe very extreme phases of matter over here, that's way beyond what we can do with the classical supercomputers. Okay, no way. Why? There are primarily 2 reasons for why that's the case. First of all, making complicated initial states for these processes, for example, very high energy protons or maybe heavy ions. There are heavy ion collision experiments. This is very difficult for us. We can do low energy proton on a supercomputer. High energy protons, they're very noisy. They're very, very hard to do. Number 2, as I said, we're doing essentially a statistical sampling of these gauge field configurations in Euclidean time. Otherwise, we cannot even do it. We have a sign problem. Everything is like oscillatory, it turned out. That's why we go to imaginary time to be able to do these Monte Carlo calculations. And as a result, we kind of lose access to these Minkowski time observables. If you're interested to know as a function of Minkowski time what happens in your final state, then you're out of luck with these sampling methods. Because in the end, as you said, it's just like a statistical mechanics. It has no connections to sort of the notion of wave functions in the states in the Hilbert space. So let me talk about these 2 issues very quickly. Let's see. Okay, there is still time. Good. So why can't we just like produce a complicated object like an atomic nucleus as opposed to just a proton on a classical computer? Well, it turned out that the complexity of these systems grows factorially with the number of quarks in them. And you may think, okay, that's not too bad. Maybe like there are like 3 quarks in a proton, and then you just like count it for a few like nuclei, okay, atomic nuclei. You would think that it's not too bad, but I would definitely encourage you to just do the calculations. So for example, if you want to do something like germanium and so on, the number of terms that you have to account for in putting into the calculations would be so huge that we would never ever have classical computers to just fit it, okay? So that's number 1. So that's a huge problem. There is number 2, there is a severe signal to noise degradation problem as a function of this Euclidean time. So for example, if you want to find the ground state from a 2-point correlation function, it's just like very similar to other contexts, like give me a 2-point correlation functions as a function of Euclidean time, the ground state is going to dominate at late times. So if I see kind of a plateau region, that would be my ground state. Unfortunately, as a function of these imaginary time, the masses or the energies start to really see a very significant statistical noise. The reason for this is actually in the properties of quantum chromodynamics. the fact that we have these light pions in the theory, and then they are much lighter than the nucleons. They actually contribute to the noise. And why do we have light pions in the spectrum? Because we have chiral symmetry breaking in chiral symmetry and symmetry breaking in QCD. So it's like very complicated phenomenology in nature in play that once we try to do these computations, they come to really bite us. And that's one of the reasons that doing these calculations is very noisy. So it actually becomes exponentially bad as you put more and more nucleons. You have to add that to the exponent of this signal-to-noise degradation. So it becomes really bad. So as a result, so far we have calculations of maybe up to 3 and 4 nucleons. And that's even with very huge masses of the quarks so that we have less statistical noise. So they're not even physical. So going beyond 2 or 3 is very hard. Okay, so we don't know how to do that yet. And then number 3 is that the excitation energy of these large atomic nuclei is actually orders of magnitude smaller than, or excitation gaps of these is smaller than their masses or ground state energies. So here is like a picture. It's like very complicated. These are 2 atomic nuclei over here. This is like a spectroscopy of those 2 atomic nuclei. I think one of them is radon, one of them is radium. At some point, I had the reference. I don't know what happened to it, but it's from an experimental paper. And then you can see that these are like kilo electron volt energies between these excitation gaps. And the masses of these objects are hundreds of giga electron volts. So it's like orders of magnitude difference in the ground state energy and the excitation gaps. How are we supposed to resolve them once we have also this exponential degradation of the signal and so on? Yes?
Shouldn't that make it easy? It's like, don't you have a Born-Oppenheimer-like separation of energy and mass scales there that should make that easy in some way?
So if you want, for example, ground state to ground state transition amplitude for these processes, it turned out that it's very important to get that very accurately because there are certain fine-tunings that are in play that if you just like miss it, you're not going to be able to like describe those sensitive observables. So unfortunately not in many cases. And then this is regarding issue number 2, again, real-time dynamics. How am I supposed to then describe what happens after these collisions, the pre-equilibriums, expansion, hadronization, freeze out, all these things that we have theoretically modeled, but not really from first principles. Okay? A lot of classical, semi-classical approximations, a lot of perturbation theory, a lot of use of simpler models in lower dimensions that go into these sort of generators of high-energy colliders that would tell us how to interpret the results, but in the end of the day, they're really just like modelings, not first principle calculations. And a bunch of dynamical response functions, transport properties. For example, if you create a quark gluon plasma, in the aftermath of these processes, how would you then measure their properties, like their transport and so on? Structure functions and so on. So here is like what I just told you. Like when we do these Monte Carlo calculations, we think about Lagrangians and actions and path integrals. So this is e to the is, which is really the weights of sampling of your Monte Carlo. If you think about the Feynman's approach to quantum mechanics, you can describe it as averaging over all the possible paths that you can take from an initial point to a final point with a given weight that is given with the e to the I times s, where s is the action. Okay? Now, when we go to Euclidean time, sometimes we can manage to turn this I to a minus and s to become completely real. So that's amazing that we can do Monte Carlo with this. But there are situations when we cannot. For example, if we go to imaginary time, but S still remains imaginary, then we're in trouble. And that's a situation with fermionic sign problem. If you have a finite density of quarks in the system, or baryons in the system, then there is no way to make this fully real, even if you go to Euclidean space-time. So you get this sign problem. If you don't want to go to Euclidean space-time, then you have to stick with this. And you have the sign problem. So these are two situations where our current lattice QCD methods based on Monte Carlo cannot help us. Finite baryon density or finite fermion density systems and real-time dynamics. That's where we need to make progress. And so far, we don't have the methods. Obviously, for these real-time dynamics problems, it's better to think about Hamiltonian language. E to the minus IHC is the time evolution operator. Give me the initial state. I hit it with this unitary operator. I tell you what the final state is, or at least some properties of the final state. That's the most natural way to describe these real-time processes. But obviously, the reason that we don't do that is the same with every problem, right? In quantum chemistry and non-relativistic electronic systems, the size of the Hilbert space grows exponentially with the size of the system itself, essentially, or with the number of degrees of freedom. We have so many degrees of freedom, and I tell you how many, I think in lecture number 2. So you get a sense of the number of degrees of freedom that we need to incorporate. So classically, we don't really have algorithms that scale polynomially with the size of the system. There are some tensor network methods that can make this possible in lower dimensions, particularly in 1D. But we're living in 3D space for these nuclear particle physics problems. So we don't really have those kind of algorithms, Hamiltonian simulation algorithms for our problems so far. Okay, so that are polynomial in size of the system, yes.
Maybe I missed this, but why would an opposite sign make the problem simpler?
Here?
Yeah.
Because, let me maybe write it down. So let's look at an operator expectation value. Let's say you want to look at the mass of a particle. This would be an O and O dagger, for example, a 2-point function. Let's just make it simple. In this language, this would turn into an integral over e to the is d of, let me write it this as field phi, instead of q and q bar and mu, just like one field phi, and then this operator, which could be a function of phi itself. Okay. So what we do is that then this is an integral over all the fields at all the space-time points. So in principle, this is also infinite dimensional. So we can't really do it. So then what we say is that let's just not do the whole thing. Let's just figure out what contributions to this integral are most important. If this would have been oscillatory, it's actually not easy to do that because things are oscillating up and down, and it is not one configuration that could be more important than the other. But let's say that I can actually turn this into Euclidean time so that this time becomes negative and this becomes completely real. Then I have e to the minus s phi. That means that certain configurations of these phi's are going to give me more of this weight, and certain are going to give me less of this weight. And then therefore, if I design an importance sampling algorithm, they would just sample the most important configurations. Then I can have a polynomial number of these configurations as opposed to all of them, infinite number of them, and get the result. Okay, so that's a good question. So that's why it's important to always turn this weight into something that is real and positive valued, so that you don't get sort of, let's say this would have been oscillatory, right? And then you get so many sort of negatives and positives that you essentially need an exponential number of samples to be able to resolve the difference between all those positives and negatives. Yes.
In your previous slides, you talk about the signal to noise ratio. What is noise in this context?
The noise in this context is, again, you have this correlation function over here. And then the noise correlation function would be something like O dagger. Okay? So something like this. So the variance as opposed to the signal itself. Now, you may say, why should this behave differently than this? This correlator, in the end of the day, is going to get contributions from the lowest excitations of the O dagger operator. And this is going to get a contribution from lowest excitations that the O operator can generate. And these two may not necessarily be the same. In fact, for this correlator, these happen to be the pions in the theory. This is the nucleon. And therefore, the noise correlator actually has a lower sort of energy contribution from these excitations than this one. So then if you just like write it down, so like do the fraction of these things at very long times, then you're going to see something that looks like, if I have this correctly, m pi minus mn times tau, where tau is Euclidean time. This ratio, if you work it out at late times, is going to be this. So this is the mass of the pions. This is the mass of the nucleons. It turned out that 3/2 of the mass of the pions minus the mass of the nucleons is a negative number. Negative time negative positive, we get an exponentially growing noise, signal to noise ratio. Noise to signal. So this is actually noise to signal. So let me put this. So this would decay if this is signal to noise ratio. It would decay like this. Okay? Good. Yes?
So the reason you said that we can't do Hamiltonian simulations is that the size of the Hilbert space increases exponentially with the size of the system.
Yes.
But as we saw here, that we are considering all the fields like in a polynomial manner. So if we just consider some of the fields, then like the ones which are more important,
Yes.
then can we still make
So the Hamiltonian simulation is not a Monte Carlo sampling, right? So it's a very different in nature than what we do with those integrals, okay? So I'll talk about this a bit more in the lecture number 2. I have actually a table of the differences between the two methods. Here, these are just functions of variables, continuous variables. So this is just like a regular integral. There is no operator, there is no state, there is no vector, there is no matrix, right? So this is like a multi-dimensional integral of functions of variables. That's that picture. Here, though, this is an operator. This is a matrix. And it acts on a vector or a state. So it's like a very different approach. And in order to then encode a matrix that is exponentially large, and all of those elements could be as important. There's no notion that some elements of the Hamiltonian are less or more. Yes, we have a sparse Hamiltonian, but in the end of the day, we really need all the elements of this Hamiltonian to be encoded to act on a state. So we're not doing any sampling. As far as I am aware, there is no like sampling methods for Hamiltonian simulation, at least not for these problems. But of course, you can use these tensor network methods with efficient ansatzer that would tell you how to systematically lower the size of the state, right? Based on the entanglement in the problem, you would just ignore certain contributions to the state. These like certain states with like Schmidt ranks of certain size. So that would tell you how to build a polynomial size ansatz for your state and be able to then look at the matrix element of your Hamiltonian within those polynomial size states. So that's one way to go. Yes.
But if you know, or like if you kind of suspect that your dynamics is like dictated by low energy states, could you try to do some Hamiltonian truncation and only simulate kind of the low-lying states in Hilbert space? So that's like another.
Yes. That's like, in fact what we do. Otherwise, we can't even do quantum simulation of this problem. Otherwise, you need essentially an infinite size problem because we have the boson Hilbert space. Bosons are infinite dimensional. And you have to truncate them based on energy considerations or other considerations. So definitely we have to do it, but your truncation cannot be so severe that you don't get the physics right. It turned out that the minimal truncations that we can think about to still get the physics right are still too high. And again, I will give you an estimate of what it takes to do these kind of problems in terms of the number of qubits and so on in a moment. But yes, definitely, we need those truncations.
Maybe I'll wait, but like, is there an effective field theory way of like systematically improving this truncation?
There are ways that people have suggested. It's more like there are two types of Wilsonian renormalization. One is like you have the blocks of higher energy and lower energy. Another one is like when you flow your matrix elements of the Hamiltonian to be near diagonal. so that you reduce the couplings between high sector and high energy and low energy sectors. Both of those methods can be used in the context of Hamiltonian renormalization. So I can point you to some papers that have a discussion of this. Good. All right, so now to quantum simulation. So now that you understand what problems we're after, where we can do classical computing, where we cannot do classical computing for these problems, let's see whether quantum simulation and quantum computing can solve some of these problems for us. Okay? So let me go to the previous one, this one. Okay. So we want to build a program, quantum computing these field theories or gauge theories of nature. Should we start from scratch? Or are there algorithms, frameworks that we can borrow from other communities? I mean, some of you guys in quantum chemistry or materials communities started to think about quantum algorithms way ahead of us. And therefore, maybe there are some similarities that we can borrow in some of the techniques and work out. And it is indeed the case that some of these quantum algorithms for simulation in particular are very generic. So we can definitely borrow them. But we have to also be mindful of the differences between our simulations and those kind of simulations. For example, in quantum chemistry, we're not dealing with a narrativistic quantum mechanical system. We're dealing with a relativistic quantum mechanical system. Okay? So we have both fermionic and bosonic degrees of freedom. Well, sometimes in quantum chemistry, you can do those as well. They're dynamical. They're coupled. They exhibit both local and global symmetries. We talked about local gauge symmetries to be very important. And we have to definitely encode them properly in the formulation. These systems are relativistic, so particle number is not conserved. So even the vacuum of a strongly interacting field theory can be very non-trivial. So we have to be able to build that very properly in a quantum hardware. Okay? Vacuum means that no net number of particles and antiparticles and so on. So in this context, you can, as I said, have quarks and antiquarks that pop out of the vacuum all the time and then turn into a gluon, and gluon turns into a quark and antiquark. So it's a very complicated mess that we have to deal with, right, in these theories. Moreover, sometimes you have lattices, right, in condensed matter systems, in quantum chemistry. Here, lattice is just sort of a mathematical tool that would allow us to do the computations. In the end, we have to take the continuum limit. So it's also very important to come up with algorithms that scale properly as we take the continuum limit or lattice spacing to 0. So this is also very important. But other than that, there are, as I said, a lot of generic quantum simulation algorithms from state preparation, time evolution, measurements that we can just borrow from quantum information community. We don't need to reinvent the wheel. Okay? But still, we have to do quite a bit of work. So there's a lot that we need to understand in terms of theory, in terms of algorithm. As I mentioned to Ken, it's very important to also think about these developments and try to push them forward as we wait for the hardware. And we don't just wait for the hardware. In fact, we have to engage in implementation, benchmark, and co-design with hardware designers, because it turned out that it was an important component of development of classical supercomputers at early ages. And it is likely that we will be able to also kind of maybe give some more insight or feedback as what are requirements for these kind of simulations. Maybe those can be implemented more naturally in different ways in the quantum hardware to facilitate our computations and eventually other computations. In fact, this is like a very nice, lively program that is happening right now with these early quantum hardware designs. They're very sort of engaged with talking with people that have applications in mind, like nuclear and particle physicists. Okay? So I will tell you examples of this if I have time. So let's see. So what are some of the questions on theory development? Well, first of all, how to formulate a standard model in the language of Hamiltonians. It might sound silly because, I mean, Hamiltonians and Lagrangians are two equivalent formulations of the theory. And it turned out that for a long time, we kind of forgot about Hamiltonians in standard model development. and I started to just work with Lagrangians and path integrals because we could do computations with them. And then sort of left the Hamiltonian developments to early days. Like Koget and Susskind are some of the famous people that wrote down some of these early papers on Hamiltonian gauge theories. And now we as a committee go back to those papers and say, oh, okay, that's a good starting point. That's not everything that we need. So we need to come up with better formulations, the formulations that maybe are most optimal towards the continuum limit. And something that is really crazy about Hamiltonian formulation is that there is not just one formulation. There are, in principle, could be infinite number of formulations because you can always give me a matrix and I can present it in infinite different bases. And it still gives me the same physics, the same expectation values. But which bases, which form, which formulations, which starting point, those things are the choices that we could make. And it turned out that there are so many different choices. And I'll tell you sort of a slide of some of these ideas that people have. How to preserve symmetry. Someone asked very nice questions about how to think about symmetries once we try to simulate these theories non-perturbatively. That also applies to the Hamiltonian formulations. Are we breaking symmetries? Are we going to recover them properly as we take the right limits? We are thinking about those questions. And also systematic uncertainties, because Ken is not going to give me an infinite dimensional quantum computers anytime soon. It's going to be finite number of qubits, even in a far term. So how do we actually truncate Hilbert spaces in a proper way, and how do we quantify the errors that we're making as a result of that? We need to build some theory to understand those effects. And we are doing that as a community, okay? So this is that busy slide that I promised. I said there are so many different starting points, formulations, basis states for these Hamiltonian gauge theories. If you're interested, these are some examples. I'm sure it's not an exhaustive list, but we give you an idea of the kind of things that people are thinking about. Discrete subgroups, pre-potential formulations, loop string hadron formulations, purely bosonic bases, purely fermionic bases, orbifold lattices, spin dual representations, you just name it. Okay, so there are so many different options. Even for a simple theory like a scalar field theory, there are so many different options. Just in like quantum chemistry, right? You can think about momentum representation or position representation. It turned out that for these gauge theories and even for scalar field theories, there are far more options that you can imagine. And the question would be, which one is the best when it comes to quantum simulation and resource requirements? And we don't really know the answer to that for many of these formulations. So it's a very active field, and people are trying to sell the best formulation they can come up with to the other group. So, okay. There was a question somewhere. No question? Okay. What about algorithmic developments? Again, the questions are now, you give me your formulation, fine, I'll accept it. Now I have to design quantum circuits to do different tasks on the quantum computers. So I need to come up with near-term and far-term fault-tolerant algorithms with bounded errors and concrete resource requirements for those theories, okay? And then I can tell you whether a given formulation or encoding would give you the reduced gate or qubit requirements. That's very important to figure out. Can we protect gauge invariance in our algorithms? One thing is to give me a formulation on a discrete lattice or whatever, and that preserve the symmetries, but maybe you do something else with it in your algorithm that would break those symmetries. An obvious example is trotterization. Sometimes we trotterize, and because of these anti-commutations, we just kind of break the symmetry, right? So you have to make sure that you understand all those violations and maybe even leverage them as you do the algorithmic developments. And then it's important to know how to do complicated state preparations, like how to prepare a proton state, how to prepare a thermal state with a finite density of some, right? So all of these things we need to figure out. And eventually compute observables. How do I get these scattering amplitudes? How do I do collision processes and look at the state of the matter and measure different observables, given that that state of matter is going to be very complicated. There's going to be exponential number of amplitudes to measure that I cannot measure. What portion of it should I measure to learn something that is physically interesting? These are all questions that people are trying to figure out at the moment. So some of these algorithmic developments, again, it's also a busy slide, but not as busy as the previous one, I guess, that you can check. And it might not even be updated, although I tried to update it a few months ago, but there's been a couple of more papers that I could have added already. So these are some of the notions of the given different simulation algorithms, what are the costs of doing some of these gauge theory simulations. So there are concrete circuits that you can go and look, and there are concrete counts of gates and so on, and qubits, and I'll mention one of them in the second lecture, or a couple of them, so that you can get a sense of the resource requirements. All of this, I should say, started from the seminal work of Jordan Lee Preskill in 2012, when they said, all right, let's say we have a fault-tolerant quantum computers, can we simulate a scattering in a scalar field theory? So they wrote this beautiful long paper, every aspect of the simulations. They did a nice resource counting, really set the stage for the other developments and gauge theories that came along later on. Okay, so if you want to start, maybe check Jordan Lee Preskill first, and then go through some of the other papers. Yes?
It's good. It's a silly question. So in principle, the processes you're trying to simulate are inherently noise resistant, right? I mean, the atomic reactions that are happening, right, or the nuclear reactions that are happening, are in some sense simulating all. I mean, the noise is a component of them, and the process you're trying to watch is independent of that noise. Ultimately,
I'm not sure what you mean by noise.
Well, what I mean is that you are taking care of a lot of noisy terms in a lot of fluctuations. Let's put it this way.
Right.
In this. So if you actually think about how one of your reactions happens in nature, right? There's a lot of fluctuations that are automatic.
Yes.
And the result you're trying to compute in the end is resistant to that.
Yeah. So I don't know in the language of kind of Hamiltonian simulation how to translate that. With these path integral formulations, what we think about, what you're saying, fluctuations, these are really sort of the fluctuations and the gauge field configurations that we sample. And it is very important that we sample properly, right? So if we don't sample properly, we lose some of the important samples. It can occur as we take the continuum limit. There is a barrier in being able to get all the important configurations properly, and we may get stuck in our sort of Monte Carlo sampling algorithms. You get stuck and you can't really jump to find the next appropriate sample. This can happen here, and it has to be taken care of properly. I think in the language of quantum simulations, it's like all the amplitudes and so on that your quantum computers would naturally add up for you. So if you give me a perfect quantum computer, I don't think I have to worry about all those sort of like fluctuations of the strongly coupled vacuum and so on.
But my question was simply whether in fact this could be used for some kind of automatic fault tolerance on the quantum computing level. That is, are there any natural kind of naturally protected codes that would well encode these particular computations that you want to do?
That's a good question. It's related to some of the discussions on error corrections using gauge symmetries. And let's say that you want to simulate a gauge symmetry or a gauge theory, and you know that you have certain local constraints because of these gauge symmetries. Can you leverage those to come up with more efficient fault-tolerant or error-corrected codes? Indeed, you can. So there are a couple of papers that will show you how we can lower sort of the requirements for error corrections if you encode the gauge theories and error corrections simultaneously. Okay, so I think that's kind of related to what you're describing, but maybe there is more to leverage for sure here. Okay, good. So algorithmic development and analog side, I mean, Ken told you a bit more about analog quantum simulation. This is also pretty exciting. We need to understand practical proposals for current hardware. Whether we can do analog quantum simulation of these gauge theories in higher dimensions. There are a lot of really nice work on analog quantum simulations of, for example, one-dimensional theories. Not a lot is happening for 2 dimensions. And eventually we want to go to 3 dimensions. What about non-abelian gauge theories? Again, there are a lot of nice experiments out there that have done things like U1 abelian gauge theory, Schwinger model, Z2 gauge theory. but not really much on non-abelian analog quantum simulations because the interactions are more complex to engineer, unfortunately. So we don't really have a very good proposal that can do this on the hardware right now, but we are still thinking about it as a community. And I guess importantly, in general, can we robustly bound the errors in the analog quantum simulations? What quantities are more robust to errors, right? Let's say that I have a beautiful larger scale analog quantum simulators that can maybe do some of these lower dimensional abelian or non-abelian gauge theory dynamics. That's great. But to what extent I can trust the final results? Can I come up with quantities that are maybe more robust? They're of like topological nature, or maybe some sort of phase transitions that are more robust. Maybe I can already learn something about those quantities and then leave sort of more, or qualities, and leave more quantitative predictions to digital and eventually fault-tolerant quantum computers. So these are all the questions that we're trying to figure out, okay, for this program. And then I mentioned implementation, benchmark, and co-design. So here it is important to understand the capability limits of the current hardware for gauge theory simulations. So we don't go crazy and come up with algorithms that are just like completely impractical, near term, far term. So we have to have an eye on what can we do today, okay? What is the nature of noise in the hardware? How can we best mitigate it? So unless we actually do computations, we cannot learn anything about this at the moment. And I think like even more exciting is this co-development, co-design program. These gauge theories have very specific interactions. Sometimes we can map them more naturally to certain interactions and degrees of freedom in the hardware. Why not leverage that? And this is in fact happening at the moment. And then maybe we can also combine digital and analog ideas and come up with sort of circuit gate-based simulations that have a little bit of features of intrinsic interactions and dynamics of the analog simulations. But then you have more flexibility to design more complex interactions because you have this gate-based approach to computing. So again, these things are also being explored at the moment in various hardware in the community. So I'm out of time. I have, I guess, 2 minutes, maybe 2-3 minutes. So, and I have plenty of slides to show you how much the community has achieved on the current hardware and different quantities, different physics of relevance to this program. You will have the slides. You can go through them, and you can spend as much time as you want exploring them, reading the papers. Unfortunately, I don't have enough time to tell you about that, but I thought I would leave the slides, okay? And so let me just like in 1 minute flash them, and then you can come back to me during the breaks and maybe say, I really am excited to hear more about this work, and I tell you. So evolution of matter, there are really interesting work. And let me say, all these hardware works, simulations, are limited to small systems at the moment, mostly one-dimensional theories, but there are some results on two-dimensional theories as well that you can see in these slides. Mostly on abelian theories, but there are some non-abelian results in these slides as well. So as a community, we're really taking all the milestones that we need to take. But we're still where the hardware allows us to be. Okay, so that's the point. So some of these real-time dynamical processes, pair creation in experiments, you can explore that in the dynamics, which is a hallmark of quantum field theory dynamics, pair creation. Studying thermalization dynamics, all these equilibration sort of mechanisms that we talked about is important in high energy physics. We can start to explore them in simple theories, even on quantum hardware, and understand things like early thermalizations, entanglement spectrum, and so on throughout the thermalization. Dynamical quantum phase transitions. This is also an interesting topic in general, but also explored in the gauge theory dynamics. These are some experiments on string breaking. So this is an interesting process. You can imagine like heavy ion collisions. There are like particles that are moving apart, and there is like a string of gluons, for example, between them. And because of confinement, as they move apart, the energy becomes larger and larger in the system. So this string at some point like snaps and then creates multiple pairs of particles. How this actually occurs in real-time dynamics is something that is really interesting to watch. and make predictions for using these quantum simulators. So these are a couple of examples of both 1D, 2D, string breaking dynamics on different hardware that all came out actually over the past year or so. So it's a very, very exciting field. We can prepare these complicated vacuum states, hadronic states. These are some results, including, for example, preparing the vacuum states of the Shunya model in a 112 qubit system. So this is one of the largest simulations that's been done so far. So you can check them out. We can even prepare hadrons, like hadrons and hadronic wave packets for scattering. So those initial states of scattering in simple gauge theories, we can start to kind of prepare them and look at their properties on a quantum computer. So this is like from an IBM system. This is from a quantonium system that I have put over here. Scattering, all this talk is all about scattering. In fact, there's been several nice hardware implementation of small scattering processes from both field theories and gauge theories. These are 4 examples that came again over the past year or so. I think this is a bit older. This is like 2024 almost, but all of these are from 2025. These 2 examples are gauge theory simulations. That is like a scalar field theory from John and group and collaborators. This is from my group. This is from a group in Munich. So it's like everywhere, right? Around the world, people are looking into this problem, trying to take advantage of various different hardware to implement these processes. These are 2 interesting results from the Seattle group, both the single beta decay and double beta decay. It's a prototype of QCD. It's 1 + 1 dimensional QCD, and it's a very simplified version of that problem. So it takes a long time before we can do this like really properly in QCD, but this is really cool. That you can start to look at these processes also with the quantum hardware, look at this dynamical sort of amplitude as a function of time for both the single beta decay and also this neutrino-less double beta decay. So people are doing all sorts of interesting things now at the moment with the hardware. Physics of Large Hadron Collider. Let me just skip these slides. I think Zhang would be more interested in these slides, but there are some sort of examples of what we can do for various real-time observables for Large Hadron Colliders. We can start to look at phase diagram of strong interactions. This like sign problem, we can evade it with the quantum computers. So these are examples of some gauge theory, sort of a Z2 gauge theory, phase diagram, some quantum algorithms that would allow you to look at the phase diagram as a function of temperature and density. This is a work from Zhangbu's group about sort of these chiral phase transitions in the presence of like temperature and density. You can start to explore them with quantum algorithms as well. These are more examples of phase diagrams of QED, transport properties. This one I really like. This is the phase diagram of, again, 1 + 1 dimensional QCD. So this is an experiment, trapped ion experiment in Maryland by Lincoln's group. And they were able to actually use the phonon modes as a reservoir to cool down the system and prepare the thermal state of the system of quarks, and then look at something like the phase diagram. So this is really nice. So there are all sort of like really novel approaches to how to do these problems in the near term in the most efficient way possible. Some other examples of open quantum dynamics for things like heavy ion physics and quark-gluon plasma studies. So these are more examples of prototype models where you can start to look at open quantum systems and movement of charges in medium in these gauge theories. And then finally, some results on co-design. Again, another busy slide to just tell you that in all different hardware platforms out there, from cold atoms to neutral atoms to trapped ions to circuit QD platforms and so on and so forth, there are many different proposals and even experiments for how to leverage different degrees of freedoms of the hardware. For example, if you have like a Rydberg atom, maybe you can implement these magnetic interactions in gauge theories more naturally. If you have phonons in the quantum computer, maybe you can leverage them to encode your boson degrees of freedom, your gauge bosons, and so on and so forth. And so this is also a very active frontier, if you're interested. And I said there are experiments too, so let me show these 3 experiments. And all 3 of them are trapped ions. Trapped ions are really leading the way on this frontier of analog digital quantum simulations. I already talked about this nice paper on preparation of a thermal state. And in fact, Ken has also similar studies in the context of quantum chemistry. So it is not just in gauge theories. We're really leveraging these cool techniques everywhere now. And these are examples of this analog digital approach to the problem. So this is a work from a group in Oxford that came out at the same time as the experiment in Maryland with Elena Green and Norbert Linke and collaborators, when we use sort of these ideas of building gates out of these phonon degrees of freedom, and then designing the circuits using not only the qubit degrees of freedom, but also phonon degrees of freedom, and then doing the time dynamics of these scalar field theory coupled to the fermions, and then look at really sort of time dynamics of these boson creations. And what was really cool in this experiment is that they could actually measure up to phonon numbers of 8 and 9. And there was like non-zero occupation in the dynamics. Even if you start from 0 phonons or 0 bosons, the dynamics of non-equilibrium quench would create these high excitations, and they were able to actually measure them. And if we wanted to use qubits for the cutoff, boson cutoffs that we require for these, we needed many, many more qubits. So just like single phonons or multiple phonons, we were able to do this like experiments very efficiently. So that was really exciting, and I think this might really mark the frontier of this co-design program for gauge theories. We don't need to just limit ourselves to the qubit degrees of freedom. Okay, so these are all examples. There are a lot in these slides, I know, but as I said, my goal was to just give you a bird's eye view of what's happening, all right? And with that, the next lecture is going to give you a little bit more specifics, a few examples of how you can set up these gauge theories, and then start to write simulation algorithms and circuits to do various things. So that would be the topic of the next lecture, all right?